Hi guys, welcome to what should be a quick video here. This is just rounding out chapter 4, and we've got just one problem we're going to look at together. So in example 1 here, we are told that American League baseball teams play their games with a designated hitter rule, meaning that pitchers do not bat. The league believes that replacing the pitcher, who is typically a weak hitter, with another player in the batting order makes for more runs and generates more interest among fans. Below are the average number of runs scored in American League and National League stadiums for the first half of the 2001 season. So we've got a data table here, kind of. It's a data table of runs for both of these different leagues in the MLB. So let's go ahead and check this data out. It is split, I meant to add this beforehand, right down through here. So you've got everything to the left of that line is the American League runs during the 2001 season in some stadium, and everything to the right of that line would be National League runs in that stadium. All right, or at least the average number for the season. Okay, so with this data, because it is quantitative, we've got an average number of runs. That's a quantity of something. Let's go ahead and go to Wabbit, and I have preloaded the data into the TI-84. I want to show you that right now. If I go to Stat, let me quit out of this. What is it doing? Let me open, initialized, open that. Let's see if that fixed it. Yeah, there we go, Stat Edit. In L1, I entered the American League data, the average number of runs for stadiums in the American League. And then in L2, I entered the average number of runs for National League stadiums in the 2001 season. You could scroll down, or I could scroll down here and double check it. I already have. But what we want to do here is go to Stat Plot, and we want to set a couple things up here. Stat Plot, as you hopefully remember, is what is going to allow you, once you've entered your data into lists, to go ahead and graph that data making histograms. I'm going to, first of all, I want to check out L1 first, just so I can keep my head together here and make sure that I'm doing something in an order that makes sense to me. L1 was the American League data, so I'm going to check that out first. So I'm going to temporarily turn off my second plot, which was the last thing I checked out, so that I'm not displaying two things at once. The calculator will give you some fits if you try to do two plots at the same time, or it frequently will. It won't always. So it's better to generally just have one plot on it at any given time. All right, so I'm going to turn plot 1 on. The data that I want for the American League is in L1, so the X list is correct. Frequency is at 1, and it will be the vast majority of the time in this class. There are a few instances you might see problems where you've got a frequency list or a constant other than 1, but most of the time you want to keep that at 1. I've chosen a histogram here. So what we're going to start to do is we're going to go to Zoom and then Zoom Stat and see what the calculator gives us. That's always a great place to start, because the calculator is, with our data in the histogram, going to give us a display that at least fits to the window well. Now, as we've talked about, sometimes the bins might be a little bit funky, and you can tell here either by taking the difference between this 8.86 and the 8.3. The bin width is currently at 0.56. You can go across and check that. Or maybe easier, definitely easier, is to just go to the window and see what the X scale is, and temporarily it's at 0.56. You can use that. It's not as nasty as some bin widths that the calculator will spit out for you, but 0.56 is not as convenient as, say, approximately 6. Let's change this X scale to 6. See if we still get a great display, and if the bin width of 0.6 works well for us, we can use that, and it'll be easier to transcribe on the axes below to make our histogram. I've got two sets of axes here below, because we're going to compare shape, center, and spread along with any unusual features for both of these distributions. Okay, so I'm changing the bin width to 0.6. For now, I'm not going to change X min and X max. What those do, let's go back to graph. We don't want to go zoom, zoom, stat, because all that's going to do, the calculator is going to reset this 0.6 I just set for the X scale. It's going to go back to 0.56 is what we originally had. You start with zoom, zoom, stat, you check out the graph. If you don't like it, you change things in window, then you go directly to graph, not through zoom, zoom, stat. So don't change X min, X max. That changes, let me show you on the graph here real quick. X min and X max are going to change the lowest X value on the far left and the highest X value on the far right that are visible on the screen. Similarly, Y min and Y max, currently the Y min is below the x-axis, which is fine. That allows us to see the x-axis, know where it is, and it gives us a sort of an anchor, a visual anchor as to where everything is. So the y-min is fine. The y-max also works because the tallest bin, the mode here of our display, the tallest peak, is still within the window. So we didn't want to change, having seen the graph, the x-min, x-max, y-min, y-max are great. In general, you will never need to mess with the Y scale. Leave that at whatever it defaults to, in general 1, and the X resolution. I have never used that ever, so don't touch that. But X scale's your go-to thing to change, and sometimes you'll change the Y max when bins get too tall. Okay, so belabored that point a little bit. Let's go ahead and trace this, and let's see if we've got all the bins within the window, and it looks like, yeah, everything fit. Everything fit. Let's double check. Highest data value you had was 11.1, and that would have been in the, would that have fit in the 10.7 to 11.3 bin? Absolutely. It would have fallen in that bin. That's where the laundry would have gone, in that close hamper right there. Okay, so now that we've got a great display for the first set of average number of runs in the stadiums for the American League, we want to see if this same viewing area, we want to see if this X min on the far left, this X max on the far right, the Y min on bottom, and the Y max will also work for the National League data. Now, why do we want to do that? Well, we want to make sure that when we compare shape, center, spread, and unusual features, that our eyes are not tricked by size differences. If, for instance, I were to transcribe this graph right here that we've got for the American League data into this first set of axes, and then I was to zoom way out, so the tallest bin for the next set was maybe only as tall as this guy right here, well, I'm going to have a hard time being able to compare the visual features between those two distributions. So as best you can, you want to make sure that you're not zooming out or zooming in on the data. Now that being said, it's not always going to work that the same Y max up top, the same Y min, X min, and X max will work for two distributions. Sometimes you will have to change that display. In those cases, you still want to make sure the bin size is the same. Okay, so we want to see if this 0.6, the difference between 11.3 and 10.7, works for all the data in the American League as well as in the National League. But the golden standard is that the window settings along with the bin width will be the same for each distribution. Okay, so done a lot of talking here. Let's see what I mean. We're going to go back to stat plot, and now that we've found good window settings for the first plot, we're going to turn that off. We don't need that anymore. Now we're going to go back to stat plot and go to the second plot here. We're going to turn this on, and this is going to use the L2 data, the average number of runs in the stadiums in the National League in 2001. We're going to turn this on. Again, note, we've only got one display on at the moment, just the second one here. But we are not going to go zoom, zoom, stat, because again, that would reset everything. We want to see if the window settings that we used from the previous display work for National League data as well. So we're going to go directly to graph, and it looks like they do. To verify that, let's see, the lowest that we go for any bin would be 8.3. Is that going to capture all of this data? It looks like it wouldn't for one, would it? It would not for 1. If we go left, it's not even displayed. Okay. So we may have some resizing to do. I didn't see that when I was setting this up. When we go right here, the highest bin goes to 11.9. That also does not capture the highest number of average runs in a stadium in the National League, which coincidentally is in a Denver stadium, which is a mile above sea level, according to the problem. This is actually coming from 36 in Chapter 4. Okay, so we've got one of those cases where we need to change the window settings a little bit. Well, we need to, of all the data values, it looks like 8.1 is the lowest. So we want to change we want to go back to the window. We want to change the X-Men from 8.3 to 8.1. Let's keep that same bin width, and then let's change the X max. Looks like we go up to 14 for the highest in that Denver stadium I was talking about. So let's change that to 14. We'll enter that. Let's go ahead and graph now. We've got a lot more bins. We've got 4, 5, 6, 7, 8, 9, 10 it looks like. 1, 2, 3. I think that's 3. That gaps a gap of 3 bins there. Okay, but the data's all there. We know the data's all there. We could trace the min is 8.1, so this guy's definitely in that. Whoop, whoop, what is going on there? Oh, that's fine. Lowest data value in the National League should be in there. The highest the bins go up to is 14.1, so the Denver stadium is represented. So it works for the second display. Now let's go back to stat plot and see if the same window setting works for the first. So this is a circular process. It's trial and error, and it gets better as you go. You refine. You just check to see if the display works for one distribution, then you check to see if it works for the other. So the first thing I want to do, well, you can go in any order, but you want to make sure that the second display is off. We're going to go to second stat plot. We want to turn the first display back on, and that's the L1 data. Again, don't hit zoom stat. We don't want to touch that. That's going to reset all the changes we've made. We're not going to go to window settings either. Those are fine. We'll just go directly to graph, and let's check just real quick to make sure that the data is represented. Now I know that it will be because the 8.1 was lower than anything we had in the American League. So yeah, the 8.3 being the lowest number of average runs per for any stadium in the American League should fit into this first bin. The highest number of average runs for a stadium is 11.1. Let's see if that's represented over here. Absolutely. We've got that highest value in that stadium, or in that bin rather. So the window settings work for both. Okay, great. Now let's go ahead and transcribe onto these axes. We want to keep the height the same for each. Okay. So the tallest bin that I'm seeing here is 4. Let's see what the tallest bin was for the other one. So I'm going to turn first plot off again, and I'll turn second one on. Go back to graph, trace, and that's also 4. Okay, so that's cool. That's easy. That makes the vertical axis easy to transcribe. And because the second one is up, we'll just use that. That's easy enough to do. Okay, so this is average number runs in the National League. Okay, and on the vertical axis we've got the count or the frequency. I'm not going to bring out a ruler to do this just in the interest of saving time. So the highest we're going is 4. Split. If 0 is the start of this axis, then we're going to have 2 approximately there. That's a little high. Do this real quick. We've got 2 right, about the same. Whatever. 1 here, 3 here. Okay, so that's decent. And then on the horizontal axis, what is the variable? Well, this is the average number runs per stadium. Maybe a better title for this display would be the distribution of average number of runs in the National League. Okay, so first bin starts us at 12.3. We've got a total of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 bins. Okay, so the 10th is going to end over here. 5th will end here. We're going to go 1, 2, 3, 4. It's rough. 1, 2, 3, 4. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so I'm violating the area principle, but that's because I'm not using a ruler as I do that. Again, just in the interest of saving time. My first bin we saw was at a height of 4. So this guy is right up there. Then we go to what looks like 2. Then we go back to 4. Then we go to 3 for the next. Then we go to nothing. Then we have a bin of height 1. Then a lot of nothings until the last one, which is a 1. Okay. So there's your distribution of those. Yeah, it's rough. That's why rulers are so important. It's much easier to interpret the data if you're using a ruler here. Let's use different color for the first distribution, and we're going to turn the second stat plot off here. We don't need that. So we'll go, this guy's on, we'll graph, and we knew this was clustered on the far left because we don't have an outlier of 14 like we do for the National League. Keep bringing that up, don't mean to. Let's trace this, double check the bin sizes. We know what I forgot to do in the last one, and we can do it because we've got access to the same bin widths and the same start point. We need to label those notches. So we go 8.1, it's 0.6 every time. So scrolling down here, let me extend the page. Put this a little bit below. We've got 8.1, this would be 8.7. So this would be 9.3, this would be 9.9. So this would be 10.5. 11.1, 11.7, 12.3, 12.9, 13.5, and then 14.1. 1. Okay, so average number runs per stadium is represented. That's the variable represented on the horizontal axis. Okay, so our second display is good. Let's go ahead and let's be consistent with the titles, why not? Average number of runs in the American League. Okay, still have the count, and we'll trying to eyeball this here. We've got 4, 2's about there, 3's about there, 1's about there, and we still have 10 bins because we kept the window size the same. So we got 10 out here, 5 should be about there, 1, 2, 3, 4. 1, 2, 3, 4. Okay, a little better that time around. And our distribution, the first bin has a height of 1. Oop. Then we go to 3. Then we go to another 3. Then we have a 4. Let me scroll up here. Okay. 2 and 1. 2 and 1. Okay, awesome. That looks good. So on the horizontal axis we have, let's go ahead and label the hash marks here. 8.1, we go to 9.3, 2 from that, 10.5, 11.7, 12.9, and 14.1. Okay, so this vertical axis, or excuse me, horizontal would be average number of runs per stadium. Okay, so we've got 2, aside from the fact that I didn't use a ruler, didn't do a great job of copying these down, we've got 2 distributions that are now very easy to compare because we kept the bin size the same, and in this case we were able to get a window that accommodated both distributions relatively well. We went beyond that. Remember, I recommended try to keep the bin number of bins per distribution to 6 to 8. We went over that in this case. We've got 10, but it's still pretty good. We didn't parcel it up too much. We didn't go too granular in chopping up our bins. All right, so for the comparison of shape, center, and spread along with unusual features, we're going to keep this verbal. I'm not going to write this down because there's plenty to say in all honesty. In terms of the shape, you see clearly for the average number of runs in the American League, you have a unimodal distribution with a mode between, if the bin widths are 0.6, this guy right here that I'm highlighting starts at 9.9, goes up to 10.5. So you've got a unimodal average number of runs in the American League with a mode between 9.9 and 10.5, and the distribution is relatively symmetric. You don't have any additional bins. But compared to the average number of runs in the National League, contrasting the shape here, here we've got a bimodal distribution with a mode between 8.1 and 8.7. And I'll highlight the bin I'm talking about for you really quick. You've got a mode between 8.1 and 8.7. You've got a second mode at between 9.3 and 9.9. Close to the same area you had a mode for the first distribution. And you have, this is definitely what I would say is right-tailed. It definitely tapers off. You've got, although you don't have a lot of data on the right side, the general trend is to have a little bit of some scattering to the right of that main cluster. On the left, where that main cluster is between 8.1 and 10.5, okay, in those first 4 bins. Okay, so recapping that, first distribution is unimodal with its mode between 9.9 and 10.5. It's relatively symmetric. Second distribution has some right skewedness. It is bimodal with modes at between 8.1 and 8.7 along 9.3 to 9.9. Second distribution also clearly has an outlier here at between 13.5 and 14.1. We know, looking back at the data table, that was the average number of runs in that one stadium of 14. So you've got an outlier. So you've got a gap then between 11.7 on this distribution and 0.6 more than 12.9 would be 13.5. So you've got a gap between 11.7 and 13.5 right in there. Okay. So there's the shape. That's how I would start with the shape. So we've got how the shape differs. In terms of the center, well, look at each. For now, we're just trying to see where could I make a vertical cut through the data so that I've got an equal area on either side. Well, because you've got such a small number of data values, let's see if we can count them. The first bin in blue here has 1. Next 2 are 3 apiece, so there's 7 data values. Then the next bin, the tallest bin in the blue distribution, is 4. And we go 2 and 1, so there's another 7. So that would put your median right there, your center, at 0.6 more than 9.3. So the center is at 9.9 in the first distribution for the American League. And for the National League, let's do the same thing with the counts. First bin has 4 in it, second is 2, so there's 6. Then we go another 4, then 3. Then we go 1 and 1. So the center of the second distribution, I believe, is going to be somewhere in this bin. So the median is at less than 9.9 because 9.9 is on the right side of that bin that starts at 9.3. So you do have the center's a little bit lower for the National League. In terms of the spread, well, we would say that for the blue distribution, the data is clearly spread and exclusively spread between 8.1 on the low end and 11.7 on the high end. We would say for the red distribution that the spread is primarily between 8.1 and 10.5. You've got a, I wouldn't call it an outlier, but you've got one stadium that had an average number of runs just to the right of that cluster between 11.1 and 11.7, right over here. And then you've got that, again, that outlier between 13.5 and 14.1. So, keys here. Let me recap what we've done. We had two distributions with the same type of data, average number of runs in stadiums. The only difference was where those stadiums were in the, did I call it the MLB? Yeah. Man, I'm so not a baseball fan. In the baseball league, in the pro baseball league. And we made two histograms, tried to keep the window settings the same. It was really important that we keep the bin widths the same. Transcribed those.